All right, we're ready to begin this week's live lecture. We're a little late getting it started, but we're getting to it this week. So looking at our calendar here, you can see exam number 2 is coming up next week on Tuesday. And as long as you're using the same proctor you used on exam 1, you don't need to tell me who your proctor is. I'll be sending it to the same proctor unless you tell me otherwise. All right, so let's go ahead and we'll put this down, this little kitty cat in the spirit of Halloween, all dressed up. And go ahead and get rid of this little heading. And set our little calendar. Oh, what we're going to do today is go over confidence intervals, sample sizes, and in the latter part of this session, I'm going to work some example test questions. And here's what I recommend you do. You might, when I get to that point, I'll tell you, and I'll say, you know what, you might want to stop watching this because it's going to be recorded. And after you've covered everything through sample sizes and spent a little time reviewing, then you can come back, jump ahead to the recording where I started going over the practice test questions. Because then you can freeze the screen, pause the screen with a recorded video, and then work those problems to the best of your ability. Then hit the play button, and then I'm going to show you me actually grading some student examples. I'll start with an A++ student who's doing everything right, plus they're getting a little bit of extra credit because they're showing off. And then I'll show some examples of some not so good students where they're making the most common mistakes I see, and then you can learn from their mistakes. But that way you can sort of grade your own work, see how you're doing, comparing with how I'm grading those examples. I think it'd be great practice to have before your exam number 2. So I'll be doing that at the end. All right, so let's go ahead, and we don't need this now. Now, just so you know, these documents that we're going to be looking at, I want you to know that you can get them from my stat lab if you go over to external links, files from the live lectures, and session 6. So we're going to be looking at all of these. So just notice that you can get copies of them. And so I'm going to begin with this one. It's a sweet short summary of how you would do confidence intervals on exam number 2. Now, the lecture notes and whatnot, I show how to do the hand calculations, and it is helpful to do a few of the hand calculations so you understand how it works. But after you've done a few, you've probably gotten all you can from the experience, because on the exam, I'm only going to ask you to use the calculator. So now when you're doing a confidence interval, it's either going to be for quantitative data or binary data. And so back on chapter 8.2, those lecture notes, pages 2 and 3, you kept reviewing them over and over and over again last week so that you can readily identify what type of data you have. Now, if the data you have are measurements, it's going to be quantitative data. If they're just names and labels, it's going to be binary data because it's categorical with just 2 categories. So for example, let's suppose you want to know what the average length of all fish in a particular lake is. So you want an approximation of the population mean. Now this is important for you to focus on because now you're approaching populations and you don't know anything about it. Nothing. Whereas before, when you were calculating those probabilities, you knew everything. You knew the shape, center, and spread of all of that quantitative data. But now you're learning some really practical statistical methods. And if you don't know anything about an entire population of quantitative data, well, I'll bet the first thing you'd want to know is what the population mean is. Remember what that represents? The typical measurement for the entire population. I would like to know, okay, what is the average length of these fish in this lake? Well, you'd like to get an approximation of it, and that's what a confidence interval is. But maybe that's not what you want to know. Maybe what you wanted to know was what proportion of all the fish in this lake are largemouth bass. Well, that's a binary data. Each fish is in one of two categories. Either it's largemouth bass or not largemouth bass. And you want to know what proportion is in the category of largemouth bass. So that's what your population proportion is, the proportion of all the fish in the lake that are largemouth bass. So you want to get approximation of that population proportion. So that's where you do this technique. Well, let's go back to the measurement, go through that one first. So all you're doing is you're getting one random sample, all right? And so what you got to know is which function to use. Let's go over the calculator. Let's turn this thing on. Now let's go where all the really good stuff is stashed, where you press the stat key, the right arrow key twice, and let's go past these so-called hypothesis tests. You're going to learn how to do these right after exam number 2. So we're going to start off with confidence intervals. And on the test, it's either going to be t-interval if it's quantitative data, or it's going to be 1 prop z-int if it's the categorical binary data. So here we are with t-intervals. So let's select that. Now we're going to have to highlight stats and hit enter if it isn't already selected. And from your sample, you just have 3 things. Your sample mean, and they're telling us that the sample mean was 8.25. And the sample standard deviation was 2.13. And the sample size was 36. Is that a large sample size? Yes, it is. For quantitative data, it's at least 30. So we have a random sample, and it's a large sample size. Okay. So the conditions are met. Oh, another condition, but this one's always taken care of, the population is huge. And we'll say, yes, it's a huge population because this lake is loaded with fish. All right, all the conditions are met for the statistical method. Now, you'll be given a confidence level. Let's say construct a 95% confidence interval for the average length of all of these fish. So you'll put in 0.95. Then all you got to do is highlight calculate, hit enter. Wait a little bit as it does all that calculating for you. Now your big job is to state this in words and in context and coherently so that anybody could understand your interpretation. Now you need to do a good job because I'm not making you do the hand calculation, and in return I expect to see a very complete and accurate interpretation and in context of the problem. So for this particular example, here's what that would look like. We are 95% confident that the population mean length for all fish in this particular lake somewhere between 7.53 inches and 8.97 inches. So you can round your final answer off at the second decimal place if nothing is said. So notice this. I make sure I get the word population in front of me so they know for sure I'm talking about the population mean, not the sample mean. We're 100% confident the sample mean's in there. It's smack dab in the center, silly. That's why it's valuable to do a few hand calculations so you realize that. Also, I don't just say I'm 95% confident the population mean is in that interval. No, I give it the context. This is for all fish in this particular lake. So that's what I mean by in context. And also you should show the units being used, right? So that's your answer that you would show for a confidence interval. Something to think about, is that narrowed down enough to where you think you have a good approximation? Because if it's too wide, then your answer is no. That's a little too wide, from 7.5 to 9 inches. I like to have that narrowed down a little more. Well, that will lead us into sample size calculations later on. All right, well, let's go over here to the world of binary data. So over here, it's binary data, so you got a sample size of 250. So essentially, you're going through the fish and you're throwing them into 2 piles. One pile are those largemouth bass. The other pile is the not largemouth bass. So try and get clear of the big, huge distinction here. You're just counting over. So then I go through and I count how many are in that pile of the category of interest. 90 of the 250 are largemouth bass. So we're going to go over here. We're going to press Stat, go over to Test, and scroll down. Keep scrolling till you find one prop Z int. So here's your inputs. X is the count, the 90. Of course, hopefully you know N is always your sample size, the 250. And then your confidence level, 0.95. That's all you have to enter. Notice there's no standard deviation when you're dealing with a binary data. You highlight, calculate, and you hit enter. Now, our job is to interpret that. So here's the way that would look in context. We're 95% confident the population proportion of all fish in this particular lake that are largemouth bass is somewhere between 30.05% and 41.95%. So notice when you're dealing with categorical data, your lower bound, upper bound are actually percentages. Well, of course, because we're trying to estimate a percentage, a proportion. So keep that in mind. But the confidence intervals, lower bound, upper bound are always percentages. But with the quantitative data, it's always whatever units you're measuring it. But this is all the things you get practice in. This is why you get practice. Let's see. Can you remind me when we use Z interval versus T interval? Yes. So let's go over here. Now, if we go over to test, let's scroll on down here. Now, what we do is we start you off with Z interval as you're first learning about it. But the reason I don't have Z interval on the exam is because to use this, you're only supposed to use it if the population standard deviation is known. And that rarely ever happens. But it was useful to start off with this because it turns out that if you have a large sample size, then there's a very little difference between using Z interval and T interval. They're very close. And that has to do with the Z distribution versus the T distribution. So if you've gotten to confidence intervals part 2, you've learned about the T distribution. If you haven't gotten to that yet, you have no idea what I'm talking about. But let's get over, I'll press Stat, go over to Test. Now, instead of going to Z interval, if I go to T interval, notice that it has S instead of the sigma. So what this is telling you is that if you're using the sample standard deviation, because you don't know what the population standard deviation is, that's why you should be using T interval. So in actual practice, we are virtually always using T interval. Because think about it. Are you going to know what the population standard deviation is if you don't even know what the population mean is? It's not. It's only in rare situations you would. Almost all the time, you don't. And so that's why we use T interval almost all the time. All right. Now, so as far as you're concerned, the test is going to be like real world. It's either going to be using the T interval, if it's the quantitative numerical data, or it's going to be one prop Z, and if it's the categorical data with 2 categories, hence binary data. And then this one-page thing summarizes that for you. Now, we're going to go over to another document here, one with a little more detail. But I'd like to start with that one because you don't get lost in the details. You'll see the big picture and you know, hey, I can handle that. But just to make sure that we understand the intricacies of it, we'll take a look at this one. Once again, it's organized. So we've got this barrier here because you got to keep it separated between quantitative binary data. So you can see the similarities and differences side by side. So keep in mind, confidence interval for a population mean versus a population proportion. And you can see how your samples look a little different. But we just worked through this example in the previous document. And of course, keep in mind, and this is very helpful to remember which sampling distribution is the foundation for the technique you're using. Because if you know that, then it's much easier for you to remember how to verify that the conditions are met, which happens to be some of the concept questions. And concept questions are easier to remember if you, rather than memorizing by rote, you've applied them and practiced them. You understand why those conditions have to be met, because these sampling distributions have to be normal. And you were working on that last week, how to determine if your sampling distributions are normal. And so that's the value why you learn that, because now you'll know how to verify the conditions. At least it'll be easier to remember. Now, margin of error, that's that equal distance you're going above and below your sample mean over here or sample proportion over there. And so if you do that a few times, now that margin of error, this may look complicated, but really isn't. This right here is the standard error. That's the size of each of the tick marks, your standard error. This funny looking thing is the critical value. That's just the number of tick marks you go. Well, if you take the number of tick marks and multiply by the size of each one, that gives you the distance you're going above and below your sample mean. Same idea over here. It's just the standard error looks a little messier, doesn't it? But that's just the size of each of those tick marks, the standard error. And this right here is the number of tick marks, the critical value. Once again, these are both doing the same thing. Number of tick marks multiplied by the size of tick marks, and that's that distance you go above and below your statistic, sample proportion, or sample mean. So it's not that complicated if you understand what each thing is doing. And the idea is your confidence level to get that. You say, well, how do you get that critical value? Well, you're not going to be working with a t distribution, but you got to use something very similar. You've done the z distribution. The t distribution, that came into play for dealing with the fact that we're using the sample standard deviation to estimate the population standard deviation. And the t distribution is what's making up for all of that. Now, for large sample sizes, the t distribution is very close to the z distribution. But for small samples, no, you got to use the t distribution. So we just follow the rule. If you don't know what the population standard deviation, you are using the t distribution for quantitative data. But for binary data, it's always the z distribution. T distribution is only for quantitative data. But you know and love the z distribution, so whatever the confidence level is, you put that in the center and find what the z-score is. This is something when you learn how to use inverse norm with a standard normal, you've done this before, and you could find that z-score, and that's where this came from. And of course, from your sample, you got your p-hat, and you'd have all the values. You could easily calculate that margin of error. Of course, you use inverse norm to get that critical value, that z-score. But once again, and just so you visually know, this is what the construction of a confidence interval looks like. It's important that you know that the sample proportion is smack dab in the center. When you're dealing with binary data, the sample mean is smack dab in the center when you're dealing with the quantitative data. So that way, when you're interpreting your confidence interval, you're not going to say, we're 95% confident the sample mean is in between. No, you say population mean. We know the sample mean's in there. So you just realize how silly it is to make that mistake. Now, this leads us into what you'll be doing after confidence intervals. And the idea is, well, what if you got a confidence interval and you don't like it? It's just too darn wide, or perhaps the confidence level is too darn low. Well, the problem will be fixed if you get a larger sample size. Getting a bigger sample size makes everything better for a confidence interval. Now, there's two things that get better. the interval will get narrower. In other words, the margin of error will be smaller. Remember, that's the equal distance you go above and below. Well, if you're not going as far, you got a narrower interval, and that's a good thing to have things narrow down. Also, you want to be very confident. So you want that confidence level to be high. Well, instead of 95%, I'd rather be 98 or 99. In case you're thinking, no, you can't have 100%. What do you have to do to be 100% confident? You have to do a census. You'd have to be measuring every single one in the population and calculating the population mean. Or over here, you'd have to be going through the entire population, throwing them all into two piles, so then you could calculate what the population proportion is. Well, hey, these are huge populations. We're not willing to do that. So you got to settle for less than 100% confidence. Now, if you look back at the formulas here, like see for E here, if you just use algebra and solve for n, you'll get the sample size formulas. Now over here, when you have really large sample sizes, the t distribution becomes a z distribution. So just turn that into a z. And we turn the s into a sigma because the sample standard deviation is close to the population standard deviation with really large sample sizes. And that's what we're talking about here, is really large sample sizes that'll make us so happy with our confidence intervals. So just so you know, it's no magic. It's just using simple algebra, rewriting those equations so that n is all by itself, and you end up with this. And over here in this row, you end up with these. So let's look at this one. So this is that critical value that we were just talking about up there. Notice it's using the z distribution because this is such a large sample size. And maybe you're using the sample standard deviation to substitute in for this, but since it's such a large sample size, it's okay. And the idea is you're given two things. So this is what's different. They actually tell you what the margin of error E is. In other words, these are your demands. You're saying, look, I want to have my margin of error E to be this small. And on top of that, I want my confidence level to be this high. So, the idea is that you're being very demanding here. This is what it takes to make you happy. Then you can use this equation to determine how large the sample size would need to be to make this happen. Okay. And then you could go out and take a sample size that large, and when you construct a confidence level of this high, miraculously, your margin of error will actually be this small. And then, of course, you'll be real happy. So you just have one equation when it's this quantitative data. Now, it might strike you odd that over here we got two different formulas. Well, the reason is that either you do have a sample proportion already. In other words, you already took a random sample, perhaps to make a confidence interval, but you weren't happy with it. It's not a complete loss because you have a sample proportion and you can use this one. And this is really the one you're hoping to use. Because this one over here is a worst case scenario, which is, okay, you don't have a sample proportion. All right, we're going to assume the worst here. And you might wonder, well, now, why is that the worst? Well, here, let me give you a little demonstration here. Let me turn on my little pen. Now, remember that when you're dealing with binary data, if you're looking at the population, all it is a bar chart. So let's suppose that, so you just got two categories. Now let's suppose my two categories look like this. Maybe this is the category of interest we call a success. This is the other one we call a failure, for lack of better names. Would you need a very large sample size before you figured out that this one category was bigger than this one? Probably not. You probably wouldn't need that large of a sample size to realize one was larger than the other. But what if, for your two categories, This is the probability of success, and this is the probability of a failure, and they're different. Are you going to need a larger sample size to tell that there's a difference there? I think you are. So that what happens is that, well, I guess the closer that are, now so the height here of that would be my population proportion. So right here. And I'm saying this is the category of interest. So that's why this is P. And of course, this is the probability of a failure, 1 minus P. Well, to tell there's a difference, you can see, well, I guess the closer P is to 1/2, the harder time I'm going to have, huh? Well, so the closer P hat is to 1/2. Well, let's see if that's 1/2. And this is 1 minus 1/2. 1 minus 1/2 is 1/2. What's 1/2 times 1/2? Well, we could go over to our calculator if you're not sure. I'll press second quit here. Oh, I got to wake up my calculator. It fell asleep on me. There we go. So you got 1/2 times 1/2. Hey, look at that, it's 0.25. So that's where that came from. This is the worst case scenario that where, oh my gosh, you're going to need the largest sample size possible. But the farther away you are from 1/2, you don't need as big. So that's why it'd be nice for you to know approximately what your population proportion is using your sample proportion. You won't need as large of a sample size. Right? So let's go ahead and let's clear that. Let's see what we got here. Let's see, there were a few homework questions without listing E. How do we find it? Did I miss something very obvious? I guess we have to know which ones you're talking about. Now, if you're working with sample sizes, you're given E. But if you're working with a confidence interval, you would be able to calculate E. Another way is that they give you the upper bound, lower bound for a confidence interval. You would just take the difference between the upper bound, lower bound, divide by 2, and you would have E. So I just have to know which problem you were talking about. All right, so let's go ahead. Oh, and then of course, now to help, because there's an important concept here. One of the concept questions asks, now, when you're changing the sample size, how does that affect the confidence interval? Now, you got to mention 2 things. Sometimes people will only mention 1, but you got to mention and be clear that, okay, if I increase, don't say this, changing the sample size will change the margin of error, the width of the interval, and the confidence level. No, you got to be a little more informative than that. Say, when I increase the sample size, here's what's going to happen. The margin of error is going to get smaller, and the confidence level will be higher. Or instead of saying the margin of error is smaller, you could say the interval becomes smaller. So now if you had a visual to help you remember that, it'd probably be easier to remember. Well, you could use this. So your sample size N is bigger. So imagine it's so big, it's big and strong, all right? Now, if it were big and strong with those big, strong arms, it could really squish in and scrunch in that interval. So you can imagine the interval getting smaller. Also, if your N was big and strong with this big, strong arm, it can lift or raise up the confidence level. So it raises the confidence level and scrunches in, makes the interval smaller. So just a little visual for you to make that easier to remember. Let's set that aside. Now, let's look at this little flow chart here for exam 2. Now, when you're taking exam 2, the question you're going to be asking yourself is, what are they asking for here? So let's address that question. You got 3 broad categories, and they're also very different. It's easy to identify which they are. If you practice this on every exercise you do from now on, pretend that you don't know which chapter you're working in, and ask yourself, now how would I know it's one of these? This is like what you were doing the past couple weeks. How do you know it's a confidence interval? Well, notice they come right out and ask for it. They actually use the word confidence interval. And how do you know it's a sample size? This one's a little more subtle, but not that hard. They're going to ask you, now how large of a sample would be needed? That it would be something very similar to that. Oh, they want me to know the sample size, huh? Notice your second question is always going to be, what type of data is it? It's either quantitative or binary. Now, this is what we went over last time, so we're not going to rehash that. Let's get into the new stuff. Now, this is basically a summary of that first document. Once you know what type it is, it's either quantitative, you know it's t-interval, or it's binary, and it's 1 prop z. And of course, if you realize which sampling distribution these are built upon, you'll know how to check the conditions. See, in order for the conditions to be met, the sampling distribution for the sample proportion over here has to be normal. For these conditions to be met, the sampling distribution for the sample mean has to be normal. And if you know how to determine that, you know how to check conditions. Oh, and be sure and mention random sample. Now let's get over here to the newer stuff. Now, what if it's a sample size? All right, just some simple questions. What type of data is it? If it's quantitative, oh, by the way, these are on the formula sheet, so we're going to look at the formula sheet too. It's got to be this one. This is the only one with a standard deviation in it. So that's how you know it's for quantitative data, because it's only quantitative data that has standard deviation. Now, if it's the binary, you got one simple question to ask. If you got a p-hat, you use the formula with the p-hat. And if you don't have the p-hat, then here you are. No p-hat, and of course, no standard deviation. Because you notice neither of these have any standard deviations, because binary data doesn't have standard deviations for its population. All right, so this is something you should review each day and actually practice applying on every exercise you do. The more you do that, the easier exam number 2 is going to be for you. So practice it. And of course, you can get this. I showed you where in my stat lab. Now, let's take a look at the formula sheet. So this is going to be supplied to you. It'll be included with your exam number 2. So you got your template for normal, CDF, inverse norm, so you don't have to memorize those. But of course, if you've got a newer TI calculator, it prompts you for those. But if you're using an older calculator like me, yeah, it's nice to have this. Make sure you don't forget the order in which to put these things. Now, you look over here, this is the center and spread for the sampling distribution for the sample mean, the chapter 8.1. This is the center and spread for the sampling distribution for the sample proportion. That was chapter 8.2. And remember, this reminds you, this is how you calculate your sample proportion, the count number that were in the category of interest out of your sample size. This right here, this is how you verify that your sample size is large enough when you're working with binary data. Now, this might look a little, now in chapter 8.2, you saw it without the p-hats. Well, that's because you knew the population proportion. But soon as you get into confidence intervals, well, you don't know what the population proportion is, do you? So what do? You estimate it and move on. So that's why we use sample proportions. Now, here's those 3 sample size formulas. So notice this is the only one with a standard deviation. So this is the only one for the quantitative data. These 2 are for binary data. When you have binary data, either you have a p-hat or you don't. Now, let's notice what all 3 of these have in common. See, they all have that capital E. That's the margin of error E. So that is always given to you in a sample size formula problem. The other thing these all have, see that Z with that funny subscript? That's the notation our textbook uses for the critical value. And for all of these, you know where you can get that? See this table right down here? Now, I can test you elsewhere. Yes, you do know how to calculate that for a given confidence level. You did that back when you learned how to do inverse norm on the standard normal distribution. But rather than make you do that every time you do a sample size calculation, I'm giving you this table. So let's suppose they tell you it's a 95% confidence interval. So you go down here to 95%, and you see this number right there? You just plug that number in for this little critical value, that Z with that funny subscript. So when you see that, oh, so that's just the 1.9600. Oh, and they'll tell you what the standard deviation is, or approximately what it is, and they'll tell you what the margin of error E is. So all you're doing is plugging these numbers in, squaring the result. There'll be a decimal part almost always, and you round up. Now that feels weird because you're used to rounding off, but let's explain why. When you calculate this, it's telling you now your sample size has to be at least this big. It's got to be this big or larger to meet these demands you made. You demanded to have a confidence level this high and a margin of error E this small. So you better make your sample size this big or bigger. And that's why we round up, but only when doing sample size calculations. All right. So what I'm going to be doing here after I go over another little study guide is I'm going to do those practice test questions, and I'll be doing examples of these. But here's another valuable study guide. Imagine having a poster board like this with all the key ideas that if you had it posted up somewhere where you walk by it each day and you say, hey, I got 10, 15 minutes. Let me just run this through my brain one more time. Because the more you do this every day, maybe more than once a day, it's going to get easier and easier for you to remember this stuff. And this stuff you're going to keep reusing the whole rest of the term. And for those of you who are going on for a second term of stats, you're going to be reusing it for that whole second term, whether that's business statistics or applied psych stats or what have you, or maybe the Math 244 with me. So it's worth it. Just keep reviewing it each day and your brain is going to start remembering. So what we've got here is, now you probably recognize these three were from that template document I gave you, and I went over how to use it last week. And so you want to keep reviewing this so you can keep straight all these distributions. So for example, in this little flow chart here, it's basically handling this part of the flow chart and the process you go through. Then, these were those 2 pages from chapter 8.2. I said, now just keep reviewing the similarities and differences between quantitative and binary data because you don't want to get them confused. The more you get this cleared, it's going to save you a lot of confusion later on. And the last missing piece is this flow chart for exam number 2. And if you've got all of this in your brain, and especially if you've been applying this one to every exercise to help you identify which problem it is, you're going to find that you're doing pretty good on exam 2. And you'll find the whole rest of the stuff we do after exam 2 to be a lot easier because we're reusing a lot of those concepts. In fact, we're going to continue to be doing confidence intervals and sample size calculations after exam 2. So you might as well learn it now. Now you say, now where can I get my hands on these documents? Because now you don't have to buy any fancy expensive poster board, though you could probably find one at the Dollar Tree, but you could just print these pages out and tape them together and pin them up. This doesn't have to be costing you a lot of money, but you could certainly make a huge difference on how exam number 2 goes for you. So I've got this document you can get with all those documents in one PDF file. So you just send that to the printer, hopefully a color printer. It makes it a little more nicer, but doesn't have to be. And just to remind you once again, let's see, did I close that? Oh, darn, I seem to have closed. Oh, no, I didn't. Phew. There it is. So going back to the main menu, you go to external links, files from live lectures, session 6. All the files are there. There's the poster board documents. So you can print those out. All right, so those are the things I really wanted to hit on. Oh, and I better mention something else very important. Ideally, you're already well aware of this, and you'll tell me, Larry, I know that already. At least I hope you'd say that. Is that, let's go to the learning modules. And the learning module, before an exam, you know it's going to have practice exams for you. So if I get over to activities, now what I recommend you, these are some extra ones, but be sure and do this one first, because this one has highly detailed solutions. It really goes over the thought processes you should be thinking about. So it might be good practice to maybe do this one first before possibly doing the ones that I'm going to be going over shortly. But then after you've learned from all your mistakes, then you've got 3 other versions if you want them, if you really want to get lots of practice. But you'll always find these in the learning module before an exam. Okay. Also answers the questions. Hey, which concept questions are going to be on there? It says right here. Now, it's the ones after exam 1. So 17 through 34 are the ones you want to focus on. And ideally, as you look at those, you should be thinking that I should be thinking about these concepts as I'm applying them, because that's what makes them easier to remember. All right, so let's see here. I'm going to shrink that down. So I am now going to begin the part where I'm going to be going over some practice test questions and showing how it's graded. So for example, I am going to begin with this one. Oh, by the way, so this is your exam instructions. So hopefully you'll write clearly so I can read. It doesn't have to be pretty, just that I can tell each letter and number from itself, that I'm not wondering, gee, which number or letter is that? I can't tell them apart. Also, I'll be showing you examples of where I give extra credit for going the extra mile. So I'll be demonstrating that. Okay. All right, so I'm going to look at these 2. So now, if you're, you can stay and watch this if you want to, but also I want you to know I will not be offended if you leave because you're saying, oh, no, I don't want to see this yet. So if this in the future, you're watching this recording, I would say now pause here and do your very best on this problem. And then I'd say, okay, have you done the best you can? Now I'm going to show you how I'm going to grade this. So I'm going to show you a student's work. I'm going to start off with a really good example, and then I'll show you some bad examples where they start losing points. All right, so here I'm going to show the solutions now. Oh, in fact, let's just take a look at this. Americans consume a mean of 1.77 cups of coffee daily with a standard deviation of 0.29 cups. And these measurements are not normally distributed. A random sample of 36 Americans is selected. What is the probability the sample mean will be more than 2 cups? Is this an unusual event? And then give 2 interpretations. So let's look at what they gave us. What did they give us here? And hopefully you're realizing in that first sentence, you'll say, they gave me everything, Larry, everything. It's quantitative data. They gave me the shape. They gave me the center. They gave me the spread. That's all that needs to be said. Why with all that information, just think of all the things I could find out. I could find the probability of one randomly selected being in any interval. I could find the probability of the sample mean being in any interval. So with that little flow chart for the exam, let's look at, now what were they asking for? It was a probability. What type of data is it? Well, we're measuring how much coffee they're drinking here. That's quantitative. How many were sampled? It was more than one. So you know it's a sampling distribution for the sample mean. You know exactly. Also, hopefully it's obvious. Probability, the sample mean will be in the interval. All right, so this is like what you were doing in chapter 8.1. And then be able to interpret it. All right? So I'm going to go ahead and we're going to go take a look at example solution. All right, so we're looking at a very good student here. Now notice my little green pluses. That means they're showing off, and they're going to get a little bit extra credit here. But you see how they clearly explained that the shape is normal and they made a picture of their sampling distribution. And you know what it is? Because they put a little bar on top of the X. And oh my gosh, look what this show off did. They even put the numbers under the tick marks. After they calculated, they know that the center is the population mean, but they calculated the standard error, the size of each of those tick marks, and used that so they could clearly identify the number under each of those tick marks. Then, because they did that, and they looked at 2, they said, oh my gosh, 2, look how far 2 would be out here. And they could figure that out by turning that 2 into a z-score. Hey, how do you find the z-score for that? Well, let's just go over here and do that after I wake up my calculator. There we go. So you take your sample mean of 2 and see how far it deviates from the center. We can see that's 1.77. And you divide it by the spread. Oh yeah, we calculated the spread over here, 0.0483. So that 2 is 4.76 standard errors above. 1, 2, 3, 4. Yeah, that'd be right about there. So this very bright student even made a picture of it. Also, they showed the probability inequality notation, even though I didn't ask for it. But they're showing the shorthand notation for this sentence here. So I give credit for that too. So they did 1, 2, 3 things that are really demonstrating their mastery here. So that's why you see 3 green pluses there. So then as they punch this in on their calculator, and by the way, they're expecting scientific notation because they can see how unusual this is. So press second, vars 2, and they put in 2. Anything big for the upper bound, you could do that 1E99, or you can just do something big. Doesn't matter. And then, of course, there's our center, 1.77. And spread, now go at least 4 decimal places so you don't have too much round off error. 0.0483. And that's what scientific notation looks like. Now, you don't want to write your answer like that. You want to write it in the appropriate notation. This is just the notation your calculator uses. Nobody else uses that. But you'll say 9.6 times 10 raised to, and the power is going to be whatever follows E, minus 7. And you can just leave your answer like that. You don't have to put in decimal. You don't have to show off like they did here. 1, 2, 3, 4, 5, 6, 7. Or if you write that as a percentage, multiply this by 100, which moves this decimal point over there, and it would look like that. But just write in scientific notation and you're good, you're golden. You've demonstrated you know what that answer means. If you write it like that, we're going to have to assume you really don't know what it means, because that's exactly what someone would do who doesn't know what it means, and they just hope for the best. Now, is that unusual? Well, yes, that's a very, very small. And now let's put it in words. So this notation, putting this in words. Here's You can see it stated here. You could also say the probability, the sample mean, is greater than 2 cups is, and then of course you could just write it in scientific notation. You don't have to write this percentage like I did there. And you could say the proportion of all the sample means that are going to be greater than 2 is, and then you could just write the scientific notation. And you can see that's what they did here. I said a little differently just so you can see it doesn't have to be exactly like that. All right, so that's someone who not only got it right, but they're getting a little bit extra credit. Now let's look at another student who didn't do as well and elaborate on why that is. All right, so here's the most common mistake in the whole wide. In fact, let's do this so you can see both. So you can still see that good answer up there. All right, so you see the standard error, the spread of your sampling distribution is 0.0483. Now, what did Poindexter do here? Well, he put in the population standard deviation, 0.29. He's treating this as though it's a population distribution. Look how wrong the answer is. And of course, they think it's not unusual. So this is a pretty serious mistake. So if someone were to say, oh, that was just a careless mistake, let's not kid ourselves. This was a complete blunder, putting in the wrong spread. You know, he completely confused a population distribution for a sampling distribution. Also, they're interpreting it completely wrong. They're interpreting it as though it was a population distribution, right? So, you know, they're losing lots of points here because they're confusing. In fact, they just took a wrong tween at Albuquerque. You know, if you go over to the little flow chart, how many were randomly sampled? They're treating it like it's this distribution when it's actually this one. They took a wrong turn. So make sure you don't do that. Learn from Poindexter's mistake here. Now let's look at another example, another bad one. Well, here they're not showing any work. Well, if you show no work, then by golly, there you have no chance for getting partial credit for what you did correctly. So that's why this person is losing more points. Also, does this sketch count for anything? No, they didn't label. I always expect to see a label there. If it's a population distribution, that's an X. If it's a sampling distribution for a sample mean, you see an X bar there. Sampling distribution for a sample proportion, you see a P hat there. If it's a standard normal, you see the Z. So you always label your curves. And just putting that in the center, I don't know whether they're talking about a population distribution or a sampling distribution because they both have the same center. Oh, now this is an example where they're garbled up the two interpretations with each other. So saying this is the probability all Americans are in that interval. No, probability is for one randomly selected. When you're talking about all Americans, that's when you're interpreting it as a proportion. So anyway, so this one's garbled up. So this says chance an American drinks more than. You left out two important words. You know, one, randomly selected, because otherwise it's not a probability. So these are really garbled up, messed up interpretations. So hence, that's why they're losing so many points. All right, so you just saw a good example and a bad one and a worse one. Now let's go ahead and look at another problem. Going over here. See what we got going on. So if you happen to be watching the recording, I would tell you, all right, pause the recording and do your very best job on this. Those of you watching live, you don't have time because I'm going over to the answer now. Before I do, let's big picture, what's going on here? Well, we're looking at systolic blood pressures. Those sound like measurements to me. What kind of data is measurements? Quantitative data. And of course, it's further reaffirmed because they're telling you the mean and standard deviation for that entire population of quantitative data. Once again, I hope you say, Larry, they gave me everything. Shape, center, and spread of the entire population of quantitative data. Just think of all the things I can find out. Like these 4 things. I could find all those things because I know everything about this population of quantitative data. Now, so you'll notice that in our little flow chart, we're all over here. You notice they're not asking for a confidence interval, are they? They're not asking for a sample size. It's all this stuff we were doing the prior 2 weeks. So, you might want to know what type of data it is. It's quantitative data, so it's entirely in this branch. So either it's going to be a population distribution problem or a sampling distribution problem. Hey, look, if you're sampling more than one, it's always a sampling distribution. It's clear and obvious as that. Okay. So let's go ahead. And with that in mind, you'll have to remember what a percentile is, because if you don't, you'll most likely mess this one up. This one is one randomly selected, so you know that's a population distribution problem. This is more than one, so you know it's a sampling distribution for the sample mean. This is finding an interval that contains the middle 75% of this population. So this is a population distribution problem. And you want to find the middle 75% of the population. And of course, you want to find the interval. And hopefully you know who can do that for you. Your good friend inverse norm. So anyways, let's go take a look at the student's work and see how it's going to get graded. So we'll start off with a good student. So 10%. So what they've given you is an area under the curve. So the first thing you do, if you're an A++ student, is you make a sketch to make sense of this. So you do a curve and start in the center, because you know that's the 50th percentile. Now, if they ask for something like the 80th percentile, you know you'd have to move to the right. But if it's less than 50% like this is, you know you have to move to the left. And you just make your best guess, draw a line, and since it's a percentile, you shade in the area to the left. Because the 10th percentile is a data value, a point on the number line, such that 10% of the population is less than. So you've got a picture of that. An inverse norm will tell you that point on the number line, that data value. Because for this interval, you know the lower bound's negative infinity. You want to know the upper bound for the interval. An inverse norm says, I'll tell you what that is. You just tell me the area to the left, the center, the population mean, the spread, and I'll tell you what that data value is, that point on the number line, the one I'm pointing at right there. So you punch that in, 67.81. Oh, and notice this. It said show the probability inequality notation. So, in fact, let me show you how you can use your sketch to make sure you get your inequality pointed the right way. So we'll just do that. So let's suppose over here you're saying, all right, my 67.81 is right there, 67.81, and my x values are off to the left, so put the x over to the left. Look at these two. Whoever's farther to the right is bigger, so that gets the bigger end. The smaller number gets a small pinched end. Put the parentheses around it and slap a p in front. And you got it. And it's not pointed the wrong way. You know you got it right. And of course, that's equal to this area, so it looks like that. So another reason to make the sketches. It keeps you from blundering up on your notation. So if I ask for probability inequality notation, you should know this is what I'm talking about. It's got a probability, it's got inequality. It's the shorthand notation for the sentence you're seeing up above there. So let me clear all those drawings. Also notice it's showing the work. Now I'm giving a plus for that nice looking sketch because it's very important to be making sketches. In fact, students who come in and they're confused on this, all I have to do is look at their sketches and then I know, or their lack of sketches, and I can understand why they're confused. So make the sketches. Now, this one says if one adult woman in the United States is randomly selected, what's the probability your blood pressure is less than 75? Now let's look what the show-off did. So they made the sketch, and they put the number under each of the tick marks. Now, do note that I do have these blank normal curves on the formula sheet. I don't know if you noticed that or not. See them over here? So you can use these to help you with those. Just be sure and label, which one is which. So I'm going to definitely give them a plus for that. Oh, they showed the probability inequality notation, and I didn't even ask for it. I'm going to give them a plus for that. So they got a couple pluses here. Now they're showing their work. Always valuable to do that because if anything goes awry, this is the only way you're going to get partial credit. No partial credit for people who don't show their work. So you can see from their little sketch, they can clearly see the upper bound is 75. Anything way off to the left is fine. So you could use 0. You could use your old negative 1E99. And then, of course, the center and spread for the population. And then punch it in. There's their answer. And here's their two interpretations, which is what it looks like for a population distribution. Now, the next one is a sampling distribution. So notice once again, they're clarifying what the shape, center, and spread is because you got to work for it. Hey, how do I know the shape of my sampling distribution is normal? Because we're sampling from a normal population. So there's your center, and they're showing how they calculated their standard error or their spread. Okay. And they even put and once they knew the spread, they went and put the numbers under each of the tick marks. Boy, that deserves a plus. But also they notice where 90 was. And once again, we could go over here and I'll have to wake it up again. And why don't we just take that 90, see how far it deviates from the center, which was the 80.5. Divide it by our spread, which is the 2.475. So that 90 is 3.83 standard errors above. So 1, 2, so that's how this A++ student knew it was way up here. And then, of course, the area greater than is off to the right, so they're probably should be expecting scientific notation. When they punch it in, sure enough, it has that number, and at the end there's an E followed by a -5, but they write it in the appropriate notation. Leaving it like this is fine. You don't have to put in decimal percentage. Oh, and it said show the probability inequality notation. So let's say that we're going to use our sketch to help us with that again, like we did with the other one. So you can see that there's the 90. In fact, I'll put it down below here. And all the sample means are off to the right. So we'll put the X bar over here to the right. And if it's over to the right, it gets the big end. Put the parentheses around it. And hopefully you see this is as good as this one here. See, X has the big end and the X has the big end. You can write either this way or that way. But this way, using your sketch, you can make sure you don't get your inequality pointed the wrong way. All right. Now, we just looked at a good student. Are you ready to look at one who's not doing so well? All right, here we go. Oh, I didn't do this one. The middle percentage. So the good student says, well, let me make a sketch of this. You know that if you go one standard deviation above and below, you have the middle 68%. So you know you got to go a little farther than that, and that's all you know. So you're just eyeballing it. But you clearly label that that's the middle 75%. Then you go over to your calculator, take the entire area under the curve, which is 1, subtract that middle percentage, 0.75. That's what's in each tail. Well, take that and divide it by 2, and you know what's in each tail. And you clearly label that in your sketch. So you're showing what's in each region. So now it's easy for you to see, okay, I can get the lower bound of the interval. I give that to inverse norm. My sketch tells me is 0.125. Put in the center and spread. For my upper bound, well, I got 0.75 in the center plus this area in the tail here, the 0.125. So the area to the left for my upper bound is 0.875. It's at the 87.5th percentile. Put in your center and spread. And so there's your lower bound and upper bound for the interval. Now, it didn't say show the probability inequality notation, but believe you me, I'm going to give you a plus for showing that. So you can see that's the lower bound. That's the upper bound. X is in the center. And that's equal to the area they gave me. Hey, do you see how you can use your sketch for that? Let me show you, just to make sure. So I know that this value right there is the 69.11. And I know this value right here is the 91.89. And where are the x's? Right in between. Okay, put your x in between. Now just compare 2 at a time, this one and this one. Who's farther to the right? You are, so you get the big end. Now just compare these two. Who's farther to the right? You are, so you get the big end. Put the parentheses around, p in front, and you got it. Notice that the inequalities point the same direction. They would never point opposite directions. If you see that, you've just seen someone who's not very good at their inequality notation. But if they had used their sketch, they wouldn't have got it wrong. Oh, and I should finish the job and show that this is equal to the area under the curve, 0.75. All right, so let's clear that. So you've just look at all the pluses they've racked up. 1, 2, 3, 4, 5, 6, 7, just on those problems alone. Boy. Now let's go on down here. Let's let a student who's not doing so well. Well, you don't see a sketch, do you? Well, that's never a good sign, because people who don't make sketches are usually miserable wretches. In fact, they used the wrong function. Oh man, did they mess up. Well, problem is they probably didn't know what a percentile was. And that was on exam 1 you're supposed to have learned that. They still don't know it. That's not good. Also, notice they completely forgot to show the probability inequality notation, so they lost points for that. So, didn't go well. Now let's look at this one over here. Now, here's what happened. For the center and spread, they got confused. They put in the center and spread for the standard normal distribution. Well, this is not a standard normal distribution. You got to put in the center and spread for your population. The 80.5 and 9.9 are what go in there. And so they got the wrong answer. Now it says give 2 interpretations. Well, you know they got it wrong. Probability that one randomly selected from the population is less than 75. 100% of the population is less than 75. Now compare that interpretation with the good one. Do you see, this one is in context. It's explaining it in the context of the problem. That's what I expect to see, not some generic interpretation like this. This is just being lazy. You want to be able to put it into words so anybody can understand it, especially because you got a context, so you put it in context. All right, now let's go over here. And let's see what happened here. Well, they forgot to put the bar on top of the X. That's a problem. And let's see, if they had made a sketch, do you think it'd be less likely they wouldn't have messed up their lower bound, upper bound here? Because doing it correctly, you're going from that sample mean to the right, to positive infinity, and they went the wrong way. Well, that's the sort of thing that happens to people who don't make sketches. If you make a sketch, it's much more obvious and clear what your lower bound, upper bound is. So, they lost points for going the wrong way. At least they had the standard error in there. That's good. But what's not good is going the wrong way and forgetting to do that. Once again, if you say, oh, I forgot the line, that was just a careless mistake. Oh, I just went the wrong way. That was careless. No, it wasn't careless. That's a huge blunder. A blunder you make when you don't make a sketch because your answer is very wrong. Very wrong. Remember what we said in that session we had a couple weeks ago? Mistakes only look careless in retrospect. Once you see what the correct answer is, then those mistakes look careless. But no, they're not careless. These are all the mistakes. You want to make these when you're doing the homework, when you're practicing and preparing for the test. That's where you make these mistakes. You make the mistakes there, mistakes are good if you learn from them. So make those mistakes and learn from them while you're doing the homework and you're learning. And then you're not making them on the test. Now let's go over here. You notice the key concept here is they're not making sketches, and that's one of the leading reasons for the mistakes. What happened to this student is that it asked for the middle percentage, and they're putting it entirely in the left tail. Also, they're thinking that, well, I did a sampling distribution, so therefore all the others must be sampling distributions. Larry wouldn't switch on me. Well, of course we would. There's no guarantee that once we go switch to a sampling distribution, everything else is. You're kind of missing the point. You're not thinking. This middle percentage, that is a middle percentage of this population of quantitative values. So it's a population distribution. And if you made a sketch like the good student did, then it's super clear what you're doing and what your lower bound, upper bound is. But they just got way off track here. Solve for something completely different. Let's see. Okay, so we just have Poindexter over here. Don't have another example. So we're going to look at another problem. Let's see here. Where did I put those? Oh, I didn't close it, did I? Here, let's put less things here. We don't need the little kitty cat there anymore. I don't need the poster board document anymore. I think I'm confusing myself with too many documents. We won't refer to that anymore, but I'm going to keep the flow chart. There it is. So now let's look at the next problem. All right. Wildlife biologists inspect a random sample of 180 deer taken by hunters in Jackson County and find 36 of them carrying ticks that test positive for Lyme disease. So the first question is, find a 90% confidence interval for the proportion of all deer in Jackson County that carry ticks that test positive for Lyme disease. Well, that might be something you'd like to know. And then the other question is, now how large of a sample would be needed if we want a confidence level of 95% with a margin of error E of 2.5%? Okay, so the first one, you state your answer in words. Second one, show your work. All right, so once again, if you were watching the recording, you would hit the pause button and do your very best work on there, trying to be like that A++ student and not like Point Dexter who keeps losing points. All right. All right, so I'm going to go to the little flow chart here. So for the first one, what type of problem is that for part A? Do you see the words right there, confidence interval? Yeah, that should be the easiest one in the world to identify. It comes right out and asks for it. Your next question is, what type of data is that? So what type of data does that look like to you? So from each deer, what are you doing? Are you measuring something from each deer, or are you categorizing? You're categorizing, because each deer is either carrying ticks that test positive for Lyme disease, or they're not. It's one or the other. It's categorical data. Oh, well, if it's categorical data, then you should just be dying to know what the population proportion is. And what is that? The population proportion of all deer in Jackson County that are carrying ticks that test positive for Lyme disease. Maybe something you'd want to know if you're hiking out there in the woods that are just loaded with ticks thanks to those deer. All right, so according to your little flow chart, binary, you know what to use. You're going to use one prob z-int to get that interval. So you see how you want to practice this every day? This is in that little poster board you pinned up. This is how you're going to know which problem is which. And you got to practice it every day and on every problem you do. How about this, the second one? How large of a sample would be needed? Oh, see those words right there? What is that asking for? The sample size. How big of a sample size you need. And notice we got two demands here. They're telling us how high the confidence level they want and how small the margin of error is. All righty, well, let's go over here. Sample size, what type of data it is. Well, we already answered that's binary data. Now, be careful on this next one. Do you have a sample proportion or not? Now, you might be tricked into I don't see one here. Well, look a little farther up. Oh, yeah, 36 out of 180. That's my X over N. I do have a p-hat. 36 divided by 180. So you're going to use the formula with the p-hat. All right? So that's how you know which formula you're going to use. And of course, you don't have to memorize the formula because you're going to have your formula sheet. You know that, oh, I'm going to use that one there. And you know what? I can just plug in the numbers because they'll give me the confidence level and I'll get my critical value, plug that in. They gave me the margin of error E. Now be careful. If it's binary data, they may give you margin of error E as a percentage. You always have to enter it in as a decimal. So, this E will be a proportion, percentage, but you got to enter it in decimal format. Same for the p-hat. It has to be in decimal format. Enter it in percentage format, your answers are going to be very, very wrong. Okay. So, our good student, let's just do the work over here and then look at their interpretation. Let me wake up my calculator. So they know to press stat, go over to test, going on down to one prob z-int because they mastered and remembered that flow chart till it's in their brain. And please don't ask me, do we get to use the flow chart on the test? Of course not, because that would tell me you didn't learn anything. You practice using that till you don't need it. You need to get that in your brain. So let's see, we got 36, and our sample size is 180. And our confidence level is 0.9. So you notice you got to enter that in as decimal. You highlight, calculate, hit enter, and then your job is to interpret that. Oh, let me show you something over here. Let me do that again. Now, sometimes I get this. A student come up to me and they say, Larry, my calculator isn't working for some reason. And I look at what they did and I see this. And I say, oh, so it's your calculator that's not working, huh? I don't know. Maybe it's user error. Because you can see that, that's not going to work, is it? Your count can't be bigger than your sample size. And so it's going to give you an error. So what would you say to a student that says, oh, that was just a careless mistake? No, it was a blunder. So once again, you got to know what these symbols mean. You should know sample size, for gosh sakes, and x over n. X can never be bigger than n. So anyways, so let's go over and look at the good interpretations the good student did. And let me resize this so we're just looking at the good student, not the bad student yet. Now, Poindexter. Well, you would call them bad. They just need to practice more. Hey, look what this show-off did. They're actually verifying the conditions are met. Remember, this is on your formula sheet. The n times p times 1 minus p hat was 100. They put in the numbers. That's 28.8. That's greater than 10, and it's a random sample. So all the conditions are met. Wow, I'm definitely going to give them a plus for that. Now, they're going to interpret this. So we are 90% confident that the population proportion for all deer in Jackson County carrying ticks testing positive for Lyme disease is between 15.096% and 24.904%. So you see, they got the word population in front of proportion, and they use the word all there to clarify they're talking about all the deer. They're not talking about the 180. They're talking about the entire population of them. And they got it in context. What a fabulous job. Another plus for that. Even though they're expected to put in context, I'm still going to give them a plus because they just did a fabulous job. Now, on the sample size calculation, so you notice they're clarifying what p hat is. The margin of error, either clarifying, oh, I'm not going to enter as a percentage, decimal, this is what it looks like. And they just looked this up off of the formula sheet. In fact, let's show that to you. So for 95%, that's the critical value. And you can see they carefully copied the formula down. So they have that there. Now they're going to substitute the numbers, so it's super clear. They know p hat in decimal format's 0.2. And there's their critical value. They put that in there. And 2.5% in decimal format. So this is showing your work. You have to show the work. If you don't, you're not going to get full credit. Hey, let's go over to our calculator. Practice punching that in. And I can punch it in just the way you see it using parentheses. 0.2. 1 minus 0.2, left parenthesis, and the 1.9600 divided by the 0.025, right parenthesis, and then the x squared. Hit enter, and there's a decimal format. You don't round off, you round up to 984 is our sample size. What that means is, you said, boy, that's a big sample size. Yeah, but you're going to be happy if you get one that big. Because if you get a sample size that big and use it to construct a 95% confidence interval for the population proportion, your margin of error E will actually be that small. So it'll be narrowed down that much. So you know what's going to cost you to have that high of a confidence level and that small of a margin of error. But your sample size has to be at least this big, at least. So that's why you round up to the next whole counting number. All right, so there's a confidence interval and a sample size problem for binary data. Now let's see what Poindexter did here. Oh no, look, they're confusing the things that apply to quantitative data with binary data. Well, obviously, they need to review that little poster board, the similarities and differences between quantitative data and binary data, so they don't get them confused with each other. Oh, no, look, they're using the entirely wrong function here. Z interval is for quantitative data, not categorical binary data. So this is a huge blunder, all because they weren't clarifying what type of data they had. Now, if they've been practicing with their flow chart and recognize as binary data, they know to use one prop Z in. And so they're not even using T interval. They're using Z interval, which is what we don't even use on this test. Oh, and then they're saying, now no, look at this interpretation. 90% chance a deer has chicks with Lyme disease is between that. This is an entirely incorrect interpretation. Let me show you what they're doing. They're trying to interpret it like it's over here. You know what? Remember over here, in order to calculate a probability, well, they're so confused, they're thinking this is quantitative data, but you could only do that if you knew what the population mean was and what the population standard deviation was. We don't know any of that. Over in this world, we know none of that stuff. You can't. So that's why, be careful you're not garbling up your interpretation like with one of these interpretations, because they're entirely different. These are saying how confident we are about our estimate of either the population proportion or population mean. And they're just got it all garbled up. So look carefully, at the interpretation, how confident we are that the population proportion is in the interval. That's entirely different than talking about the probability of one being an interval. That's so far off. Over here, let's see what happened. They did not recognize, they forgot they had a p hat, so they're using the formula without one. So they're using the wrong formula. Also, they got a little confused here. When they see that alpha divide by 2, they said, oh, am I supposed to divide it by 2? No. Don't you see that is the very same symbol as over here, that whole thing is replaced with this number? They obviously have not practiced these problems enough, that they're making a mistake like that. Because, if you're making a mistake like that, you're going to get every single one wrong on your online homework. Also, this is a common mistake. They did not convert their 2.5% to decimal. And if you do that, look how wrong your answer is. Could that ever possibly be a sample size? No, something is obviously wrong. But you can see they're making all sorts of errors there. They didn't notice they had a p hat. They got confused with this notation. They're dividing this by 2, messing it all up. And they forgot to turn this into a decimal. Lots and lots of mistakes here. Oh, let's look at another one. Now here, they're saying they're 90% confident the sample proportion is between 15% and 25%. No, we're 100% confident the sample proportion's in there. Smack dab in the center, silly. So that's wrong. But also they didn't state it in context. Once again, look how the good student. It's all in context. So they're explaining it so anybody could understand it. Because here they're just being, not only being lazy, but they're being wrong. Lots of problems here. Let's see over here. They forgot to use p hat, but at least they didn't do any dividing by 2. They remembered to put in decimal, so that's good. Oh, they left their answer like that. Well, that's not a sample size, is it? So they forgot to round up. So they lost a point for not using p hat, and they lost half a point for leaving their answer like this, not rounding up. All right. Oh, we got one more problem here. for you to practice with. All right, a random sample of 15 one-year-old baby boys in the United States had a sample mean of 25.5 pounds and a sample standard deviation of 5.3 pounds. This distribution of weights is approximately normal. Oh, by the way, approximately is good enough. What are they giving us? Well, let's see. Now don't be confused. This is what the mean they gave us was a sample mean, a sample standard deviation. Oh, okay. And there's a random sample of size 15. So, and notice we're measuring, weight here. And so it's this quantitative data. So let's look at what they're asking for. Find a 98% confidence interval for the mean weight of all one-year-old baby boys in the United States. I hope it's super clear what you're being asked to find here. They came right out and asked for it. A confidence interval. Let's go take a look at our little flow chart here. So obvious, it's a confidence interval. They didn't ask you to calculate a probability. They didn't ask you how large of a sample size. They asked you for a confidence interval. What type of data is it? Well, we're measuring how much these kids weigh, these boys. So it's quantitative. So now you know it's going to be t-interval. But you might wonder, but Larry, 15 is a small sample size. That's less than 30. Can I do this? Well, there are two ways your sampling distribution for the sample mean could be normal. See, that's how we verify the conditions are met for this method. The sampling distribution for the sample mean has to be normal. And of course, we have to have a random sample, which we do. Now, we don't have a large sample size, but are we sampling from a normal population? We are. So if you're sampling from a normal population, well, by golly, your sampling distribution is always normal. So we're good there. Now, it's a small sample size, so it's extremely important we use the t-distribution. Well, we're using t-interval. So let's go ahead. Oh, let me wake up my calculator again. Likes to get sleepy on me. There we go. And so we'll go press stat, go over to test, and go to t-interval, not z. Z-interval would be very wrong here because it's a small sample size, so it'll be too far off. Highlight stats. So what was our sample mean? 25.5. What was our sample standard deviation? 5.3. And what was our sample size? 15. And what confidence level? 98, so 0.98. Then we just highlight, calculate, hit enter. And then we just need to put into words correctly and in context what that means. Okay, and that's so we'll look at that. In fact, why don't we go ahead and show you what the good student did. Oh, what did they do? They point out it's quantitative data. We're sampling from a normal population, so it's okay that the sample size is less than 30. Random sample, conditions are met to use t-interval. You believe you me, I'm giving them a plus for that. I'm impressed. Now, they're going to put this in words. We are 98% confident the population mean weight for all one-year-old baby boys in the United States is between 21.909 and 29.091 pounds. Notice they put the pounds in there. The only thing you could say is, they didn't put a period. Well, I'm not going to mark them down for that. They did a fabulous job. They got the word population in front of mean. They put it in context. They used the word all to make it super clear. We're talking about the entire population. Fabulous job they did. Now let's look at the sample size. Now, how large of a sample would be needed here? Well, let's see. They want a confidence level of 99%. Ooh, that's pretty high. margin of error of just 1.4 pounds. Ooh, that's pretty small. They're being pretty demanding. So they're going to approximate, they're going to tell me approximately this. Now, we're kind of fudging here a little. Normally, we would take a large sample size. And from that large sample size, that sample standard deviation be a good approximation. So we're kind of fudging here because normally you wouldn't expect 5.3 to be doing a very good job, but we just want to make you give you something here so you could calculate it. But just know in actual practice, we would make sure we use the sample standard deviation from a large sample size. So let's go over to the formula sheet. Which one are you going to use? Well, maybe we should start with the flow chart. It's a sample size, what type of data it is. Oh, yeah, that's right. It's the only one with a standard deviation in it. So you know that it's this one here. So you copy it down carefully, and you get your confidence level, 99%. So that critical value there is going to be 2.5758. And all the other numbers are given to you. All you got to do is plug them in and calculate it. All right. So let's go ahead and see what our good student did. Hey, let's go punch it in on our calculator. So we'll have the left parenthesis, the 2.5758, and that's going to be multiplied by the standard deviation they gave us, and divided by the margin of error. So this is 1.4 pounds. Now remember, this is the quantitative data. It's not being given to you as a percentage. You don't have to move any decimal points. Sometimes students will get confused and start moving decimal points around. They're not thinking carefully enough about what they're doing. Right parenthesis and then square it. Hit enter. So it has to be at least this big or bigger. So you got to round up to the next whole number, which is 96. So now you know, if you would get a sample size of 96 instead of 15, well, first of all, you wouldn't have to know if your population's normal, would you? No, you wouldn't, because you'd have a large sample size. But if you use that sample to create a 99% confidence interval, lo and behold, your margin of error E will actually be this small. It'll be narrowed down that much. And boy, you're going to have a confidence interval you'd be proud to own, because it's giving you a really good approximation because it's so narrowed down with such a high confidence level. And you see, that's not so bad. Look how high. That's awful close to 100%, isn't it? And that's pretty narrowed down. And it's just 96. That's because these sample means are clustering in so close to that population mean. So hopefully, somewhere along the line, you're getting a little more appreciation for how good a job the sample mean is at estimating the population mean, if it's from a large sample size. All right, let's look at some not so good examples. All right, they're using z-interval. Well, that's really bad because this is a small sample size. So it's going to throw your answer off too much. So only z-interval is only if the population standard deviation is known, but it is unknown. So you got to use t-interval. So 98% confident, the mean, we don't say mean by itself. It's either the sample mean or the population mean. If you don't tell me which one, I assume the worst. Or you don't know, and that's why you didn't say. Is between, and of course they didn't state it in context. They didn't even put the units in there, for gosh sakes. So this is, not doing too good. So these are all the sort of mistakes you want to avoid. Let's go over here. They didn't copy the formula down carefully. Now that's just careless. Oh, a careless mistake? No, it's a blunder. Okay. Now, because they forgot to square it, does the sample size of 9.75 sound at all reasonable? No, it doesn't. So, they should have caught the mistake because it's not even reasonable because that's way too small. They didn't even round up. So there's numerous mistakes here. All right, so avoid all those mistakes. Let's look at this one. look at the interpretation. Once again, they're interpreting it as a probability of one randomly selected. Once again, they're interpreting it like it's over here, but it's not. It's over here. They're getting these interpretations mixed up. They haven't practiced the interpretations, and they're really not clear what they got everything all garbled up. They're not practicing it. They're not clearing it. They're not using that little poster board enough every day. Okay. Now, look at this. Show your work, and they didn't show the work. Well, that's going to cost you, only half credit, and they didn't round up either. So, they lost 3.5 points for not showing their work, and another half point for not rounding up. They're not doing too good. All right. So we've covered all the bases here, haven't we? My golly, we've done these population distributions, sampling distribution. We've done t-interval, 1-prob-Zian, and we've been doing these sample size calculations. Plus, you've got an idea of how the scoring is. You've seen some mistakes being made, so you can make sure you avoid those. Because I showed you some of the most common mistakes that show up, and hopefully you will avoid those. Okay? Well, so this was, not only covering these last topics, but this was also your review session, because I was doing those review problems and actually showing you how the grading is. So, let me see, I put the calendar away. Let me get that back up here. Let's see if I've got that here handy. Here we go. So we've got the test on Tuesday. So we're not going to have another session before the test. This was our review session, but I will be having a session. It'll be sometime after exam 2, because I want to give you a heads up on how to do the hypothesis tests, because they're very important. In fact, when statistics comes up in your future coursework and in your career, what you're going to see more than anything else are hypothesis tests. So it's really important that you're good at these. So that's why I want to make sure I do a session after exam 2 during next week to get you on the right foot on that. All right. Well, that's it for our session. So if you got any questions, feel free to ask away. Well, I close this. If you've got any questions, you can type it now. Give you time. No, doesn't seem to be any. All righty, then we will see you next week after exam 2. Of course, if you're coming to my exam, I'll see you there.